All right, so I have David Neivandt and Greg Simms joining me to talk about this project with the Neivandt Research Group, Team NRG, at the University of Maine, discussing a sustainable biodegradable composite material derived from waste lobster shells and a natural binder. So guys, thanks for joining me on the podcast today. Before we get started, maybe a quick introduction. We'll start with yourself, David.
Sure. Thanks, Jonathan. Yeah, so my name is Dave Neivandt. I'm a professor of chemical and biomedical engineering at University of Maine. Been here for about 25 years now. You probably tell from the accent I'm Australian originally.
No.
And most of my research focuses on engineering new material systems with a heavy focus on trying to utilize waste materials and low value materials to valorize them.
Greg?
Excellent. Yeah. Hi, my name is Greg Simms. I'm a staff member at the Advanced Structures and Composite Center at the University of Maine. I've been with the ASCC for about 5 years, working on the SMART program. It's a collaboration between the University of Maine and Oak Ridge National Laboratory, and we're focused on the development of natural composites and their manufacturing technology. I'm also a PhD candidate, working on, with Dave as my advisor. We've been working on this research since 2023.
2023.
That's right.
Interesting. So I've got to share this. This was an article that I found. Lab cooks up new uses for leftover lobster shells. Interesting title to an article. So if you would share a little bit about on the background of this. Started back in 2023. Give us a little background on the research and why. What led you to look at the viability of lobster shells as an alternative for biodegradable type composite applications?
Oh yeah, happy to, Jonathan. It's a long and convoluted story, but I'll keep it fairly succinct.
Sure.
It actually started back around 2011, quite a long time ago.
Okay.
When the director of the Lobster Institute at the University of Maine, of course, UMaine has a Lobster Institute.
Yeah, makes sense up in your area.
Yep, exactly. So Dr. Bob Bayer, so he brought to me an idea that had come to him from one of his former graduate students to try and make a biodegradable golf ball out of lobster shell. And the idea there was to really take a waste material from the fishing industry, which is typically landfilled, and make a product out of it, a golf ball in particular, that could be driven into the ocean with a single shot and wouldn't pollute, unlike a regular golf ball. And it would have the advantage of returning the lobster shell back to the ocean. So that was the idea. And I had an excellent undergraduate student in chemical engineering at the time looking for a research project. So we started work on this. And so our design constraints obviously were something that's environmentally benign, that biodegrades in water comparatively rapidly, and had to withstand being hit by a golf club at about 100 miles an hour.
Right.
So we trialed various natural matrices and eventually found one that worked. We just ground up the lobster shell and made a composite with the lobster shell as a filler. Compression molded some balls, and yeah, they performed extremely well. We were able to fire them off steel plates at 100 miles an hour and have them rebound perfectly.
Wow.
Yet they would dissolve in water in about 2 weeks. So very unusual set of physical
That is
properties.
incredible. Yeah.
Yeah. So we licensed it, although it was never actually produced commercially. And so it sat dormant for quite a while until the SMART program, as Greg mentioned, this Department of Energy through Oak Ridge National Lab program, was looking for composites with profiles that match this material very well. And their interest was in temporary structural applications. So at that point, we picked the research back up again, and Greg joined as a PhD student. And I'll let him carry the story on from here.
Yeah.
Sounds great. So again, the work we were doing with the SMART program, you might be familiar with BioHome, the 3D printed home we did.
Yeah.
lot of that's a product of the SMART program, where we were looking at housing applications, and there was a kind of an adjacent call to look at materials that could meet structural applications, but were very temporary in nature and rapidly biodegradable. And so David proposed that we use this material in that application. I was, as a staff member working on the project, just immediately interested, and asked if I could volunteer in his lab to help the process get going. And the first part of it was we needed the ability to produce the material on at least at the lab scale in a very consistent method. So we couldn't be doing hand layups anymore. We had to get into injection molding. And so the first project we got into was there an injection molder or an extruder on the market that would allow us to make test specimens? Mm-hmm. And so we did a number of searches and trials with companies. And in the end, we had to work with the university's Advanced Manufacturing Center to make a custom injection molder, which is actually a log splitter that got converted. We took off the cutting head, put on basically a plunger, and then they created a barrel. Okay. And then a series of test molds. And so I was able to produce, tensile specimens and flex specimens and compression specimens, all with this injection molding technology. And I could do it very consistently over time. Obviously, at the beginning, there was a lot of trial and error, but our formulation got pretty quickly up to speed, and we were able to start making things very consistently. Right. And so being a construction project, we had to compare it against something of a known value. And so we chose Eastern white pine. That's a traditional building material in the Northeast. It has been for centuries. And so there's a lot of data about it. And so we started doing our tensile tests and flex and compression. And in the end, the base formulation, in terms of flexural strength, was just, about 10% low in where we needed to be. The compression strength was actually almost on par. And so when I say where they needed to be, Eastern white pine in terms of flex properties, it's about 59 megapascals in terms of strength.
Yeah.
Our base formulation just out of the gate was at 50 megapascals. So we were very close in flexural strength. And in compression strength, you look at 33 megapascals for compressing Eastern white pine parallel to the grain in its strongest direction. We were, with the base formula, we were over 65 megapascals in terms of strength.
Okay.
And that was just the base formulation. And the reason why I bring up flex and compression is when you look at construction, those are your two main design keys for building materials. You're in a building, you're very almost never in tension. And so those are the key attributes we're looking at. So right out of the gate, we were very strong in terms of those aspects. But we wanted to, that was the base formula that kind of came out of the work that Dave and the group were doing from the golf ball. And so we wanted to figure out all the different variables that are leading us to these. And so we made, in the first set, we made just a series of changes, 6 changes amongst those initial process conditions. Mm-hmm. And we found when we increased the process temperature, it was only by 10 degrees that we got another 20% boost in terms of flexural strength. Just out of that, we hadn't really done much in terms of material optimization yet. And so we got a good boost there. And so that work has continued on. And I would mention that in terms of flex properties and compression, we're about the 70 megapascal range in terms of strength. Your standard concrete is around 40 megapascals in terms of strength. So when you think of a material that's like this, it's an all natural material, and we're already stronger in strength in concrete and construction lumber. So we had a pretty impressive material set right off the bat. Right. Once we started to go look at solubility of the material, this is the materials being completely immersed in water for periods of time. We've gone all the way up to 6 weeks, but untreated, the material again kind of meets that standard of about 2 weeks you're down to nothing but lobster shells at the bottom of your immersion beakers, with really nothing left. And so that's a great thing if you want it to go away. But if you're building a temporary shelter like we're going after, it's not the best thing. And so we're starting to look at expanding the horizon in terms of its durability over time.
Sure.
And also the immersion test isn't really very accurate to the real world. So the other thing we're doing here in the summers, we'll do what we consider a rain event, right? And so we'll do, a rain event for 5 minutes and 10 minutes and 30 minutes and an hour.
Right.
And then we'll test the wet strength of the material at that point to see how viable it is in that.
Quite a bit different than 2 weeks underwater, right?
That's right. Yeah, right. Yeah, given the time to like get it wet and then give it time. And we also need to do that, like, let's get it wet today, let it dry for a day, and get it wet tomorrow, those sorts of things. Yeah. It's more real world type application there.
So why I'm curious real quick, why the Eastern White Pine again? Is this, why did you start with this building material?
Again, so Eastern White Pine is a traditional building material in the Northeast.
Okay.
So if you look back to the time when the settlers came over, in the 1600s, they raved about the giant Eastern White Pines that were available on the East Coast. And so a lot of the early buildings that are done there are all Eastern White Pine, and they took a lot of pine back to Great Britain to use as ship's masts. And so in terms of traditional timber buildings, a lot of that is Eastern White Pine, at least early on. Yeah. And then even today, as the lumber section has moved on to more southern yellow pines or Douglas firs or the other materials that are there, Eastern White Pine in the Northeast is still considered part of the SPF or spruce pine fir designation for dimensional lumber that you could buy at the store.
Okay.
So again, it's a relevant building material. And there's a ton of, we can go to a lot of the engineering wood handbooks that have been produced by the Forest Products Lab as engineering guides. And there's lots of data about Eastern White Pine, all the specifications that we need. Whereas other woods don't necessarily have all the tensile and compression and flex data available to them.
Right. Interesting. And you had mentioned, I won't get into the details of the binder, the resin, but you can give us kind of a brief overview of that if you would.
Yeah, for sure. So what we do tell folks is it's an all natural binder. It's a byproduct of the agricultural industry. Again, natural product, dissolvable in water, and it's essentially a thermoset. A thermoplastic material.
Thermoplastic. Okay, it is a thermoplastic.
So it allows us to do this, and I think one of the early issues on why the technology didn't necessarily have commercial success early on is because in this process we dissolve the binder with water, and so that's not traditionally used in the plastics industry.
Right.
And so I think when it went out, the folks had just trying to get their head wrapped around how you going to produce this stuff. You don't traditionally go into a plastic shop and see a lot of water.
Yeah.
So that was kind of the hold up. And so part of the work that we're doing is making it manufacturable to do the testing, but also de-risking the technology so that it can, when the next time it goes out for licensing, it could be more successful.
Sure.
In terms of a licensed product. And so we talked about solubility. Let's get back to construction. So we wanted to see if it would work with traditional construction connectors, so screws, nails, and adhesives.
Oh yeah.
And so we went out to Lowe's, bought all four of the categories, came back to the lab. We inserted screws and inserted nails into test specimens. And then we went over to our jigs and we did a traditional nail withdrawal test where you hold the fixture down and you try to pull it back out.
Right.
And we compared that against dry wood and also wet wood. And what we found is the the lobster shell composite is on the order of about 2 times stronger in terms of holding a nail or holding a screw. And in fact, on the first pull, we broke our test fixture because it lodged so hard into that. We weren't expecting what it was, so we had to convert.
Right.
And so we did that, and then in terms of glue adhesins, right? I did your traditional wood test where you glue up samples and then you try to pull them apart. And what we found first is the material is compatible with off-the-shelf construction adhesives,
Okay.
which was great, right? I can go out and use traditional adhesives with it. But then the stuff is kind of at this point in my research time, I had spent hundreds of hours in the lab making the stuff and then cleaning my dishes.
Mm-hmm.
And what I knew from cleaning my dishes was that it's hard to clean. And so I took from that maybe I should try to use this as the glue. And so I took my test specimens of the composite and I used hot water and I glued them together with just hot water. And when I did that and conducted the very same test, what I found is the bond strength was 11 times higher than a commercial construction adhesive.
Interesting.
Yeah. And I got my grading was over 10 megapascals, which is that's the rating of a structural grade bond. So think of your epoxies and a lot, much higher level systems that are used. And so here I have a natural material that I've glued together with just hot water. I've got a structural grade bond. That was a pretty big, exciting point for us. We're moving on to more. And so then of course for buildings, everyone's concerned about fire. And so we did fire tests, and we had to conduct the test twice just to confirm our results. But the material is self-extinguishes in a matter of about 2 to 3 seconds. So when you apply flame, it does not burn. It starts to char, but then once you remove that flame, it just goes out on its own. And so there's no rate of burning. And so that part of it was all worked well. The last part for us that we had to work on was our shear tests, and it has a much higher shear value than construction lumber. So what we found there in terms of our is this material applicable to buildings, we kind of checked all the markers in terms of it met the strength qualifications, met the burn qualifications. The only thing we were working on is solubility in that. And so we continue to work on solubility. We have found coatings that extend our life in water. I have some results that show over a 2-week period where you get this 40% solubility of the material of the total system. We've got it down to less than 10% with just a very simple coating system that we use. And then we have other things that are still in the works that we're trying to explain at this point to extend the life even farther than that. So,
wow.
I may add a couple of other pieces of that?
Absolutely, David. Yeah.
Yeah. So part of the end of life story. So solubility is one possible route, and of course that stems from the golf ball. But also, interestingly enough, we have proven that it's biodegradable and meets the qualifications for a biodegradable material. So that was verified by a third-party laboratory and showed that it degraded in terms of CO2 evolution was the metric, but degraded completely in 31 days out of a 90-day test. And passed through, I think it was a 2 millimeter sieve hole. So it is biodegradable. And Greg's also shown that it's compostable. And so we've done some home composting, not commercial composting, but home composting. Sure. And shown that it loses about, I think it was 65% mass over about 7 weeks.
Yeah.
Wow.
And I would mention too, in that third party study, we also had them evaluate the soil health before and after. Again, we're making a lot of claims about how good this product is, and we want to back that up in terms of what happens when it hits the soil. And what the lab that did the test for us is a very well known soil fertility lab, soil health lab, and they do this testing mainly for plastics companies that want to market their product as biodegradable. And so we said, yes, we want to be compared against plastics. How do we stand up? And so again, we met that standard in 31 days, but we also found that we improved soil health when we biodegraded. We actually added, because of the lobster shell, we're adding calcium to the soil, which in some areas of the states is very important. They're lacking, and we also added some nitrogen to the soil from the proteins that were available. Yeah. So we had that, and they gave us the classification of no management is required. And when they say that to a farmer, it means you don't have to do anything additional. You don't have to counteract this in any certain way. You're actually you're doing right by your soil health. And what that also meant, with as fast as it went away, is that we were actually improving or exciting the microbial community that was consuming our product, right? And so based on those test results, that led us into another area of research. Before I head on to that area of research, I want to stop and just ask Jonathan, are there any questions about the structural part of things?
I am real curious what specific applications would in building, because I'm assuming we're talking mostly building materials right now.
Right. Yep.
And these would probably be indoor type applications in building. What would we initially be looking at for?
Yeah, so my research is focused on tackling the challenge of refugee shelters or homeless shelters. So temporary applications where you have disaster situation, whether it's conflict or natural hurricane or otherwise, where you need to rapidly deploy shelters. And you don't necessarily need those shelters to last for long periods of time.
Okay. So these are more or less temporary type shelters. Yeah.
And so we're working towards being able to 3D print the material.
Wow.
And in that application, we could do on site. Yeah. And with all of these materials, you think about particularly lobster shell, and we think there's other shells and materials that we can put in this, but if we just focus on crustaceans, right? About 80% of the world's population is going to live near a coastline by 2050.
Right.
So if you had a situation where you had a disaster in one area, you could deploy a system to a disaster zone. You either come preloaded with your materials, or you collect materials from the given area, and then you start rapidly producing building materials.
Yeah.
So that's kind of the concept in the terms of building space, particularly to buildings, but also coming back to the ASCC, they do large format printing there. In large format printers, the printer does not print its own support material that you would typically see in a small scale 3D printer, right? A little desktop printer. If you tell it to make an arch, it's going to print the support for the arch out of a different material, then it's going to come back and actually print your arch. Well, that's all good and well for small printers because that material is easily washed away. But in a big printer, you don't have that. And so all of that support material becomes waste.
Right.
And if you're not using a thermoplastic material, that's a landfill waste that you're going to. So what we're also working on, the research for this year, is to use this lobster shell composite as the support material. So think of, you have a material that's this natural material we can put in, and then we can take and recycle, or if we do internal type of structures that need support, we can then wash the support material out of a large structure. And so that becomes a much bigger deal when you start to think of the print volumes that we have at the ASCC, where our print beds, exceed 100 feet in some directions. And so
how do you source on the feedstocks from the lobster shells? Where do these, because I know a lot of these come from, this is refuse that that is discarded, typically goes to landfills or what have you, from everything from restaurants to you name it. I mean, so how are you sourcing these, and who are you working with?
Yeah, for sure. Yeah, right now we have a great partnership with a company out of Southern Maine called Shucks Maine Lobster Company.
Okay.
And Shucks does high pressure processing.
Mhm.
and their main consumer are chefs across the country. They're
Okay.
able to process lobster. Through the high pressure process, they remove the proteins or the meats from the shell.
Mhm.
That is now a clean product. It's still in the raw form because it's not cooked. And they're able to send those out. And because of the high pressure processing, they're able to have a longer shelf life. So that once they seal it, it has about a 30-day shelf life, so they could get it all over the country, and chefs have plenty of time to work with it.
Wow.
But also a benefit of that process is it's so efficient at removing the proteins from the
Mhm.
shell that it provides a very clean product
Yeah.
that's great for the work that we're doing. And so what they do is for us, they do a little bit of drying and then some hammer milling to send us some smaller pieces. And then once we get those smaller pieces, and they're just stored in 5-gallon buckets, plastic, within plastic bags.
Yeah.
We take them out and we do a secondary round of grinding to get them to a kind of standardized size.
Mhm.
And then I'm able to use them directly.
Wow.
So it's really, if you can, now we're kind of at research grades, but we're working with shucks and working with our funding partners to figure out, as we start to scale things to make this, larger and larger, what are some opportunities for scale, both within shucks, and then we'll eventually we'll have to start thinking about around the East Coast. But
Right. Very interesting. Wow.
so those are the parts in terms of structure. So while we were doing a lot of the temporary structure work, then we got a small grant from Sea Grant to do some adjacent tests. We said, hey, we think we have some ideas for some small scale commercial products that are not included in our current funding mechanism. So, can we go try some things? And what we wanted to try were the golf tees and seedling pots, and then an update to the golf ball.
Yeah.
And so, with the help of the AMC, we went and produced these molds and started to test things. And the seedling pot has always been I think Dave and his original group, they had that idea, and I just pulled that out of their literature and said, hey, let's make a mold of it and see if we can use it. And then the golf tee was kind of just a natural fit from the golf ball itself.
Yeah.
And in both
the sealing pot, describe. Did you say sealing pot?
Seedling pot, yeah. So you think about those little typically the pots that gardeners will use to start seedlings in the springtime.
Okay,
so
gotcha.
Little 2x2x2 little pot to start your seed and get your seedling going.
Yep.
And from those two concepts, both the golf tee and the seedling pot, and also the data that we got out of that third-party lab, what we're starting to converge on or move on to is that not only do we have a good structural material that's can degrade naturally, but we also have the opportunity as a nutrient delivery vehicle.
Yeah.
Is what I like to call it, right? I can now take these products that are intended to degrade, right? And now we can use them have a functional use, and then also have a purposeful post-life use, right? I can take my whole seedling pot, put it in the ground, and everybody's happy. The plant and the soil microbiomes. And so the same thing with the golf tee, right? I can take this over to a golf course, particularly those, what we're finding is out in the Southwest, there's a lack of calcium. So we could take the lobster shell loaded golf tee that has a lot of calcium in it and use it as a golf tee. When it breaks on the course, even better for the golf course owner, right? Because now we're spreading calcium across his grounds.
So no one ever picks those up. They just leave them after they break. So they just sit there.
That's right. Yeah, that's what we're finding. And so, right. So now we have these two concepts for those vehicles. And so it kind of just has continued to evolve from there. We've had interest in folks for fishing lures. We've had we're doing a USDA study now to use the lobster shell composite as, again, in a pellet form to deliver biochar to the soil at a regulated amount. In our hypothesis, will help to remediate PFAS from soils.
Sure.
So biochar has a lot of surface area. It's very effective at allowing microbes in the soil to grow larger communities. If we have the opportunity to use our technology to, one, put them into the soil where they need to be, where the biochar needs to be, next to the plant root. Not only, one, do we give it a good home in terms of biochar, but we also give it all the nutrients in that package to feed the microbes to help them do their work. The remediation path that we're working on is take long chain molecules, use the microbial community to break them into short chains. Short chain molecules are able to be absorbed by plants. And then we can take those plants off the land and dispose of them properly in a landfill.
Yeah.
So thereby remediating, taking the PFAS out of the soil and putting it into a landfill.
Wow. And you said
Dave,
earlier that
yeah,
you were, at some point, you're hoping to be able to 3D print.
That's correct. Yeah.
Great.
So yeah, in terms of 3D printing, so again, we mentioned that this is a very wet process. And that is, again, not something the 3D printing industry is very used to.
Yeah.
There are small scale gel printers. But the one gel printer that we had at the ASCC for a period of time, I clogged it on the first run because the needle points were too fine for the lobster shell particles.
Okay.
And those gel printers are really made, they're small scale, and they're not the scale that you would print a structure out of. And so in our work, as we continue to de-risk the manufacturing technology for injection molding and extrusion, we're also thinking, okay, how would I feed a 3D printer with this material? And so this next year, part of the funds that we receive from the Department of Energy will go towards your kind of a stationary 3D print head, to where we'll extend our lines from our manufacturing equipment, and we'll have a movable table, right? So we'll have just a continuous extrusion of material through the nozzle, and we'll move the table, move the print bed, as you were, to be able to start printing simple shapes. From that work, that'll help us develop the understanding that we need to go on to then put that extrusion head onto a robotic arm and have the robotic arm start to move. So that's the stuff that's kind of out in the future.
Yeah.
But
yeah, we'll just add, though, that, Greg, you have done some manual, if you like, 3D printing and shown that we do get good bed adhesion, we get good bead fusion.
That's right.
So it looks like it is potentially viable.
Yeah, for sure. Yeah, we did everything kind of the same way that when 3D printing got its start back in the 80s. All right, that was out of a glue gun, and so using that same thought process, I just took a syringe and I did my syringe work, and all the kind of tests that we look for at the ASCC in terms of any material that you're going to print with. Can you adhere to a print bed?
Yeah.
Once you do that, great. Now, once you put one layer on top, does your bead hold up? Make a good bead. Great. We passed that one, and then can you start to stack beads without your whole thing collapsing? And so we passed all of those kind of very rudimentary tests, and so that gave us the confidence to go ahead and start to think like, okay, we can think about printing this down the road. And then in terms of manufacturing technology, we've been using our kind of custom-made setups, but we also wanted to see if we could use some already industrial machinery that are widely available in the commercial space to produce the material. So I went down to Lystrit's extrusion company in New Jersey, and got on and set up a day with them. And within about 30 minutes, their technicians, we had the system running. We had the material coming out of the twin screw extruder in a nice bead form. So we have good confidence that we can produce the material on an industrial scale using industrial equipment.
Yeah.
So that part for us is good. It doesn't, twin screws are kind of hard to work with in terms of injection molding because they don't produce a lot of pressure, but the twin screws extruder will also allow us to do more profile type extrusion. Like if we wanted to get into more board production, we could do that. And maybe even 3D printing. We'll see.
Yeah.
That'll help us in terms of that front.
So what's last question for you guys, because we're wrapping up here, but what's
Sure.
the last to take this from the research that you've done into scalable commercialized type application project, like you had mentioned these temporary shelters, what is the next step in that for you?
So for us, what we're Dave and I are currently working on with a couple other students is we've gone through University of Maine's it's actually NSF I-Core and also University of Maine's MIRTA programs. Both of those are entrepreneurial mentoring programs, and we're using the golf tee as the reintroduction of this material back out into the market.
Yep.
We want to, again, a lot of the work we've been doing is trying to de-risk the technology. So when it goes back out into the market, we have success there. And so we've been going out over the last, Dave, this is the past 2 semesters we've been working on this for the business side of it. And what we've been doing through those 2 programs is really customer discovery. Is there a market for such a thing? For a golf tee that's made out of lobster shells. And if there is a market, are people willing to pay for it? All those. That's
a good question. Like what from a price comparison, in golf tees, there are different price points for everyone. Like, right? I mean, there's people spend a lot, people spend a little. I guess it really depends on the level. So.
Depends on the material largely. So the wooden tees are by far the most popular. And the plastic tees are less popular, more durable, of course, and more expensive. So,
that's right. Yep.
So we're in the process of trying to figure out, what is our price point if we do scale up. What price can we produce them for?
Yeah.
So that's where we're at. And so Greg mentioned we're working with a small team. So I have an undergraduate senior biomedical engineering student, Isabel Irani, who's actually leading us through the MIRTA program. And then we're fortunate to have a woman who's about to graduate with her MBA from the business school here at UMaine. Michaela Reynolds has joined the team as well. So we've got quite a bit of varied expertise in the group and trying to assess the path to market currently.
Absolutely.
Yeah. And just, in terms of for the industry, I think it's Dave and I are not entrepreneurs. we want to make we want to continue the development on this product, get it going, but we also want to make the next round of natural composite materials. We're just dealing with 2 right now. It's really just 2 materials. There's a whole breadth out there that we could work with.
Right.
And so we're really excited about that, but we also want to make sure that the material doesn't just sit in the lab. We want to
absolutely
get it, we want to get it out there. And
there's
so this
real world applications. Yeah, absolutely.
Right. Yeah. We want companies to come and talk to us and, whatever they have another application that they think we could use the material for, great. We'll help de-risk that, the golf tee or others.
Yeah.
Again, I think that's the exciting part now is like, we're ready to pass this one on.
Yeah.
So, anyways.
And you think about,
one last thing, if I could, is
go ahead.
We're wrapping up here, Jonathan, but so related to this, another variant of this material we've been working on for the last 3 years or so is actually a foamed composite. And so we've actually,
you say a foam? A foam?
Yeah. So we've actually managed to aerate the material.
Okay.
And produce a quasi equivalent for expanded styrofoam.
Oh wow!
So we've matched the thermal insulating properties. We've matched density, compressive strength, impact strength, etc. So
wow!
So we have another variant of this, which with completely different physical properties, still has very rapid dissolution, dissolves in about 4 days. And again, we're looking at ways to control that to potentially. Make it hold its form a little longer, but basically the idea is that we have a thermally insulating impact absorbing material that instead of polluting and remaining in the environment for hundreds of years will degrade in water in about 4 days in a very benign profile.
Dave's trying to work on his next episode.
Well, it does sound like a separate one where we can discuss for sure.
Flame-based material, though.
That's
right. Well, I love it. I am always fascinated. I love when I talk to, any of the team at the University of Maine when they come on and share some of the research and the work that they're doing. So I really do appreciate the both of you coming on today. This is really fascinating. Is there a link that I can point listeners to? I think we found some at UMaine or some links that we can showcase. But if you have anything that you would like to send over to me that I can highlight on our show page, and even if there's, I didn't even check to see if there's a video on YouTube of some testing with these, but any stuff like that, I'd be happy to showcase on the show page when we publish this next week.
Yeah, for sure. I would say just to date, we haven't published a lot. We've been working on doing a bunch of research, and I've been slow in getting my publications out.
Yeah.
And so that stuff will be coming, that sort of stuff will be coming forthcoming, but I would say connect on LinkedIn, because a lot of anything that has been published about the events we've been at or talks we've given, it'll all be on there. And then they'll also have an easy link to when we start publishing other future data or future videos.
Good.
We'll add too, just to close out, we're participating in the MRTA demo days here in the second week of May. And so there'll be I think a press release and some LinkedIn notifications related to that. So people are most welcome to come in person, meet us, or please just reach out via email too.
You said that's the second week of May, demo day?
I think it's the 13th, if I remember correctly.
13th.
Right.
Okay. Yeah.
At
We'll try to
UMaine
find something
Boston
on that. And if we can find something on that, we'll include that on our show page as well.
Fantastic. But failing that, please just look me up on the university website, Department of Chemical and Biomedical Engineering, and shoot me an email.
Thank you both. David, Greg, thanks for joining me again today. Appreciate your time, and hope you have a great weekend.
Yeah, you too.
Thanks so much, Jonathan. You too.
Yeah. Hold tight real quick, and I'm going to end everything.